your screen?
Sure. Can you see my screen?
Yes, sure. We can see.
Yeah, I'm going to full screen mode right now. Can you see my slides moving?
Yes.
Good.
So,
Yeah.
okay. So our next speaker is Sayan Mandal. He will talk about detecting inflation from primordial magnetic fields with CMB surveys. So you have more or less 45 to 50 minutes, but we are not too much formal about timings. I will give
Sure.
you a reminder when you will have 5 minutes left. Please go ahead.
Perfect. Yeah. Thank you so much. Thanks for inviting me to give a talk about this topic. So this is a problem that I worked on a couple of years back. So magnetic fields is something that I've worked on during my PhD. So we have been discussing or working on different aspects of magnetic fields, mostly how we can detect primordial magnetic fields, and I'll give a motivation for why we think primordial magnetic fields exist. We've been focusing on how we can detect magnetic fields through various observational tools that we have. And the whole thing starts because we detect magnetic fields at different scales in the universe. Um, and the source of some of these magnetic fields is more or less well understood, whereas on larger scales, the sources are not at all well understood. Now, we have local magnetic fields. So anytime we have charged particles moving in a plasma, we have magnetic fields. And that's something we understand, like how magnetic fields in stars and suns and all of these things come about, or even in smaller scales. But there are micro Gauss level magnetic fields in galaxies, and their sources are unknown. So these are correlated on large enough scales that we don't understand how magnetic fields correlated on those scales come about. And the hypothesis is that their origin can be due to either of the three things. So far, there are three mainstream proposals. The first is that these magnetic fields could have originated during inflation, or they could have originated during an early universe phase transition. And the third thing, which is more or less known as the astrophysical scenario, is that these magnetic fields were generated at a much later stage after galaxies formed. So it's not an early universe generation scenario, but they were generated by galactic dynamos, which are charged particles moving, magnetohydrodynamic effects of moving plasmas. And they were later amplified by all of these processes and became those large-scale magnetic fields that we see today. So scenarios 1 and 2, which are generated during the early universe, these are what are called primordial magnetic fields. And the basic idea is that you generate nano-Gauss level magnetic fields on megaparsec scales in the very early universe, way before structures, any kind of structures formed in the universe. And then when structures started collapsing, structures started forming by the collapse of dust clouds, these magnetic fields, which were on megaparsec scales, they got adiabatically compressed to a shorter region in space, and to a smaller region in space, and they were compressed to a micro-Gauss scale magnetic fields in galaxies. Now, as I will argue, if we can detect inflationary magnetic fields, so if we can be sure that any primordial magnetic field we detect is coming from inflation, that will be a smoking gun evidence that inflation happened. So let's talk a little bit about these scenarios of magnetic fields. Now, primordial magnetic fields from inflation, they arise, and there are different models corresponding to different models of inflation as well. And they arise from vacuum fluctuations during inflation. So we know that vacuum fluctuations during inflation lead to the formation of structures in the later universe. So those quantum fluctuations can explain the large-scale structures that we see today. And we also know that inflation can generate gravitational waves as well from tensor perturbations of the metric during inflation. You can also have vacuum fluctuations of hypermagnetic field, and these survive through the electroweak phase transition to give rise to the magnetic fields. Now, inflationary magnetic fields, if you generate something during inflation, they will by default have a very large correlation length because inflation is generating all these fluctuations and they are pushed to superhorizon scales and they are later re-entering the horizon. So inflation is stretching everything out to have very large correlation lengths. Now, typically, if you wanted to generate a magnetic field, we know that the Maxwell tensor F mu nu F mu nu, that is, has conformal symmetry. So any magnetic field generated dilutes with the expansion of the universe, and you'll not have significant magnetic field today, even if you amplify by later local magnetohydrodynamic processes. But if there's a scenario where the Maxwell tensor is coupled to the inflaton field or to the curvature of spacetime, and it breaks this conformal scaling invariance symmetry of the Maxwell tensor, you can generate magnetic fields of sufficient strength because they don't dilute as 1 over a square with the expansion of the universe. So it doesn't scale with the square of the scale factor of the universe. And there are different models. In fact, there are dozens and dozens of models that come up with predictions for primordial magnetic fields during inflation. The other feature that we'll have is if magnetic fields are generated during inflation, they have a scale invariant or a nearly scale invariant primordial magnetic field power spectrum. And I'll define formally what a power spectrum is. It's very similar to the scale invariant spectrum for matter perturbations that we get from inflation. Now, let's say primordial magnetic fields are generated during inflation. So these scale invariant magnetic fields, which are generated above 0.1 nanogauss on megaparsec scales. So if we have magnetic fields correlated on megaparsec scales, as I mentioned, these will be adiabatically compressed to microgauss fields in galaxies. And this happens because of magnetic flux conservation. We know that the magnetic flux through any region or through any surface has to be conserved. So magnetic field scales as 1 over magnetic field scales as 1 over area. So let's say we start out with a megaparsec scale structure of dust clouds, which later collapses to a 10 kiloparsec scale structure, which is the typical scale of galaxies. So if it was initially harboring a magnetic field of 0.1 nanogauss, after collapse due to flux conservation, that magnetic field strength will rise to 1 microgauss. And this is the typical scale of magnetic fields associated with galaxies. So if somehow we are able to detect scale invariant magnetic fields at 0.1 nanogauss or larger, that will be evidence of inflationary magnetic fields. And that's because other scenarios of generating magnetic fields, they do not generate a scale invariant magnetic field, and they don't have the sufficient energy to generate magnetic fields at 0.1 nanogauss or higher on megaparsec scales. So there is no other known mechanism now to generate magnetic fields at these strengths and on these scales. And hence, it'll be a compelling evidence for inflation because, as I just mentioned, there's no other way to generate such a strong magnetic field correlated on such large length scales. However, if we can't detect magnetic fields above 0.1 nanogauss, but rather constrain them to be below 0.1 nanogauss, then what we learn is that inflation isn't the primary source of galactic magnetic fields. There has to be some help or amplification from dynamo mechanisms. So maybe inflation generated the seed magnetic fields, which are later amplified by dynamo mechanisms, or maybe inflation played a much smaller role than we are thinking about as far as the galactic magnetic fields are concerned. Now, the other scenario is called the phase transition magnetogenesis scenario. The idea is that there's an out of equilibrium first order phase transition, which is typically needed to generate magnetic fields. And the two main phase transitions, the so-called phase transitions that we know about in the standard picture of cosmology and particle physics, is that when the universe had a temperature about 100 GeV, few picoseconds old, we had the electroweak phase transition, which led to the Higgs mechanism. And we had the QCD phase transition where the free quarks and gluons got confined into baryons and mesons. So there are different models which can explain the generation of magnetic fields from these phase transitions. The problem is that in the standard model of particle physics, these phase transitions are not first order phase transitions. In fact, the QCD is not even a so-called phase transition. It's more of a crossover from one phase to the other. So all these models require some beyond the standard model extensions to make these first order, and they have different observational consequences as well. The other issue is that there's been no evidence of any of these beyond the standard model extensions to beyond the standard model extensions so far. So not only from the scenario of magnetic fields, but from the phenomenological side as well. So this causes us to slightly prefer magnetic fields from inflation because the scenario is slightly less ad hoc in a sense. Now, you can also generate magnetic fields from galactic dynamos. So dynamo processes are just moving plasma, and there's this feedback, nonlinear feedback between velocities and charges in a plasma. You can generate magnetic fields. And if you're generating magnetic fields from dynamos, this cannot explain the 10 to the minus, I'm sorry, there's a typo, it does not explain the 10 to the minus 6 Gauss magnetic fields. No, sorry. This does not explain the 10 to the minus 6 nanogauss, so 10 to the minus 15 Gauss magnetic fields that we observed in voids. So as I started mentioning, that magnetic fields are not only there in galaxies, but these magnetic fields also exist in clusters and superclusters of galaxies as well. They're correlated on much larger length scales, but their strength is much, much smaller. The other remarkable thing is that even when we look into the voids between galaxies, it's also more or less uniformly filled with a magnetic field, which has a lower bound of 10 to the minus 6 nanogauss, so 10 to the minus 15 Gauss, depending on the length scale. So there's it scales with the square root of inverse length. But this distribution of magnetic fields, this lower limit, which is obtained by looking at TeV blazars, so how many photons you observe from TeV blazars, or the non-observation of photons, you can put a lower limit on that. So this was a work done in 2010, and it was later improved in 2018. So there's a strong lower limit on what's the strength of the magnetic field and how uniformly it's distributed in the voids between galaxies or clusters of galaxies. And there is no way that magnetic fields, which are generated locally in galaxies from dynamo processes, can explain the magnetic fields in these voids, because then you have to have some mechanism which pushes out the magnetic fields from the galaxies and uniformly fill the space between them, which is very hard to come up with. And this is something that leads us to strongly favor the primordial scenario and more or less the inflationary scenario. Now, how can we constrain inflationary primordial magnetic fields? So let's say if magnetic fields are generated via inflation, these are existing, it's part of the cosmic plasma, it's affecting the magnetohydrodynamic turbulent processes that are going on in the early cosmic plasma all the way to recombination. So the presence of the magnetic fields, they will induce temperature anisotropies and polarization anisotropies in the CMB, because the presence of magnetic fields, they are adding a contribution to the stress energy tensor, which in turn are causing perturbations. And there are also Lorentz forces, because magnetic fields will move charges around in a slightly different way than if there were no magnetic fields. So that will introduce some cross correlations between E and B modes, T and B modes, and they'll also have polarization modes. So you'll see their signatures in the spectrum. Now you can go ahead and take an inflationary primordial magnetic field model, or you can just take a spectrum, and then you can calculate what the CMB spectra will look like. And the CMB spectrum scales as the fourth power of the magnetic fields. On the other hand, primordial magnetic fields can also have another effect on the CMB, and that's after the formation of CMB. So what happens after recombination is that the plasma becomes neutral. The magnetohydrodynamic processes stop because now we have the universe filled with neutral atoms. And the magnetic field which existed in this plasma, which was being heavily processed by MHD processes, that suddenly becomes frozen in until much later when structures start forming and there's some feedback between structure formation and magnetic fields, but the magnetic fields get frozen in. Now, after the CMB is formed, the CMB photons are freely streaming. So they are passing through these magnetic fields which just got frozen in. And the magnetic fields are strongest right after the formation of the CMB, because after that they're diluting with the expansion of the universe, with the square of the size of the universe. So these CMB photons, which are passing through the magnetic fields just after recombination, their plane of polarization of these CMB signals that we see, they will be rotated. And this is what we call Faraday rotation. So anytime electromagnetic waves pass through magnetic fields, their plane of polarization is rotated. So we'll see Faraday rotation. And just because the CMB distribution is anisotropic, the Faraday rotation, a plane of polarization rotation, which we also refer to as birefringence, that will also be anisotropic. So if you look at the CMB sky and detect the plane of polarization rotation, this will typically just be like a statistical random Gaussian fluctuation of how much the plane of polarization is rotated. The nice thing about Faraday rotation or birefringence is that the birefringence spectrum will scale as the square of the magnetic field, which means that we can get a much stronger constraint on magnetic fields from birefringence than we can from looking at the T, E, and B mode polarizations or the temperature anisotropies. So birefringence can provide a tighter bound on the magnetic field strength from future surveys. So if somehow we can look and constrain the error bars on anisotropic birefringence in the universe, we can nail down or put a much tighter constraint on magnetic fields than we can from CMB spectrum. Now, how do we model these inflationary magnetic fields? As far as their observational effects are concerned, we say that the co-moving magnetic field is a Gaussian random field in 3 dimensions. So information about the energy of magnetic fields, this is encapsulated in what we call the power spectrum. So magnetic fields can be non-helical, or magnetic fields can have a certain amount of related helicity. And helicity is not important for our discussion, but helicity is basically the parity dependent nature of the distribution of magnetic fields. So helicity is defined as the volume average of A dot B, and A is the magnetic vector potential. So if you have a non-helical field, the helicity is definitely 0. And helicity is important for CMB because helicity affects how the magnetohydrodynamic turbulence happens, because how the magnetic field strength decreases or how the correlation length of magnetic fields evolve when through magnetohydrodynamic processes, that depends on how much helicity you have. But this is not important for birefringence because magnetic helicity can be shown to not affect birefringence at all. So it totally depends on the strength of the magnetic field, and that's it. And the strength of the magnetic field is encapsulated in the power spectrum. And traditionally, the power spectrum is written somewhat like this. So the power spectrum is written as a power law. So power spectrum as a function of the wave number is some sort of a power law k to the NB. NB stands for the index for magnetic field power spectrum. And the traditional way we write it, and I'll show a diagram very soon, is that it linearly increases or decreases up to a damping or a cutoff scale, after which turbulent processes cause a damping and there's a sharp fall of magnetic field power spectrum from that finite value to a 0. Now for inflationary magnetic fields, we have NB equals -3. Just like matter power spectrum, this leads to a scale invariant power spectrum for inflationary fields. On the other hand, if you have phase transition generated magnetic fields, you have to have causal magnetic fields, which means that magnetic fields are not correlated. So the correlation function of magnetic fields will become 0 on superhorizon scales. That leads to a power spectrum of k squared at the minimum. Now, we set KD. Typically, the KD is set to the silk damping scale, and because you can argue that magnetic fields on scales smaller than that, they cause no net rotation because they cause no net rotation because they're not large scale enough on those small scales. The strength is not large enough to cause any discernible rotation of the plane of polarization. Now, what we do is that we don't take this traditional power spectrum, but the traditional power spectrum gets modified a little bit because of these turbulent processes. So if you model the evolution of magnetic fields from their generation all the way up to recombination, you'll see that the magnetic field power spectrum, even if you start out with a simple power law, it gets modified at what are called inertial scales by the effect of turbulence, because our cosmic plasma was extremely turbulent and it was charged as well. So we have all these complicated MHD processes, which sort of modify the traditional spectrum from this power law form to a slightly more realistic form. So in this realistic form, you have on large scales, this k to the NB dependence. But on what are called inertial scales, this is modified to a k to the minus 5/3, or sometimes a k to the minus 2 form, depending on what your initial conditions are, the type of turbulence you are considering. So this is what is called a Kolmogorov spectrum. K to the minus 5/3 can have a steeper spectrum. So what's important here is that there's a redistribution of magnetic energy from slightly smaller scales to slightly larger scales. So on larger scales, if you have a larger magnetic energy, that will mean a larger rotation of the plane of polarization of the CMB spectra that we can observe. So it'll give us a better handle to detect anisotropic birefringence and hence inflationary magnetic fields. So we can use this spectrum to theoretically calculate the amount of birefringence that we can expect given a certain power spectrum of primordial magnetic fields. Now, to construct the birefringence spectrum, this is defined in a way very similar to the temperature anisotropy in the CMB. So you look at the birefringence at a particular direction, another direction, take the correlation function, average it over the entire sky, and you define your CL alpha alpha to be your anisotropic birefringence spectrum. From this, you can calculate the amplitude of anisotropic birefringence, which is an L-dependent quantity. So it depends on the multiple that you are looking at, L plus 1, CL alpha alpha by 2 pi. Now, the other thing is that this amplitude of anisotropic birefringence, which scales as B squared, which we already talked about, the other important, interesting scaling is that it scales as the fourth power, inverse of the fourth power of frequency at which we are observing. So this gives us a remarkable way to understand anisotropic birefringence, or the source of anisotropic birefringence, because there can be other things that can lead to anisotropic birefringence as well. There's some other physics as well that can lead to anisotropic birefringence. But the thing about magnetic fields is that the rotation of the plane of polarization of something, of a photon, that's proportional to 1 over frequency squared, and hence the amplitude is proportional to 1 over frequency to the 4th. So even without knowing the plane of polarization, the initial plane of polarization, if we can look at the rotation at 2 or 3 different frequencies, we can immediately find out what the strength of the magnetic field is because of this 1 over frequency to the 4th dependence. Now, for a scale invariant magnetic field, which is typically what's generated during inflation, this amplitude of anisotropic birefringence is typically independent of L, or it is an extremely weak dependence on L for small l. So for L's less than 10 or 20, it doesn't really depend on L. So it's more or less a constant function, which is very good because we can compare, we can do a calculation and compare different multiples. So this frequency dependence is going to be interesting because if we are using different CMB surveys to observe the anisotropic birefringence, we need to look at least 2 different frequencies, and many CMB surveys observe at least 2 different frequencies. So now our calculation, so if we go to our anisotropic birefringence spectrum, which we calculate using our power spectrum, magnetic field power spectrum, we get this dependence. So the question is, what's the frequency that we should use for this calculation? And the answer is that we can construct an effective frequency from the 2 different frequency channels. So we can take 2 different frequency channels at which these surveys are observing, and we can construct an effective frequency just by taking some mean of the inverse fourth power, construct an effective frequency, and observe at that frequency. Because when these different CMB surveys are giving us a constraint on the value of A alpha, then that's a frequency independent quantity that they're talking about. And this we can calculate at this effective frequency. So this is like taking an arithmetic mean of the measurements on the two channels. The only assumption is that we are assuming that there are equal noise levels. And we know that if you look at the different surveys like Simon's Observatory or CMB-S4 or the future proposed CMB-HD, we know that for the 90 hertz and 150 gigahertz channels of observing the CMB, the noise levels are more or less equal, and this is an assumption that we can make and construct this effective frequency without much issues. So taking this expression, for 90 and 150 gigahertz, we find an effective frequency of 103 gigahertz. So we'll calculate this amplitude of anisotropic birefringence for this effective frequency, and then we'll compare it to the constraints that these observations are putting out. Now, the error bars on A alpha, these are given by the different CMB experiments. So Simon's Observatory gives an error bar on A alpha of 2.4 times 10 to the minus 4. CMB-S4 improves it by 2 orders of magnitude. And CMB-HD, which is also another proposed CMB observatory that's planned to be constructed in Chile, that reduces it by a little bit more. So it takes us all the way down to 1.4 times 10 to the minus 6. So by comparing our expression to these error bars on A alpha, we get the following constraints on the magnetic field strength. So Simon's Observatory will say that the magnetic fields are constrained to be 0.47 nanogauss. CMB-S4, with this A alpha, the magnetic fields will be constrained to 0.08, whereas for CMB-HD, this gets further constrained to 0.036. And this number is going to be extremely important. So if we are asking what's the signal to noise ratio for observing a scale invariant magnetic field at 0.1 nanogauss, you'll see that Simon's Observatory will give a signal to noise ratio of 0.2, which is not very good. CMB-S4, on the other hand, improves it to 1.25, and CMB-HD, because it's 0.036, takes us to a signal to noise ratio of 3, which means that even the current best constraints on the strength of scale invariant magnetic fields comes from these E, B, and T CMB spectra from Planck and SPT analysis. They give us a sigma BI of 1.2 nanogauss. So this is above the level of 0.1 nanogauss that we want. CMB-HD can bring it down to 0.036 nanogauss, which means that it can improve the bound on A alpha by 4 orders of magnitude and gives us the tightest constraints on the CMB so far, on primordial magnetic fields from CMB so far. So this is the thought that I want to focus on a little bit. So we have the strength of the scale invariant magnetic fields, and we have the coherence length of magnetic fields. And since it's scale invariant, this strength is a straight line along this axis. Now, so far, the best constraint that we have from CMB is this following. So the joint Planck 2015 and SPD 2015, the 2 sigma upper bound is at 1.2 nanogauss. Now, in this green region, if the magnetic fields are detected to be lower in this green region, then we don't have a 0.1 nanogauss scale invariant magnetic fields, which means that even though the magnetic fields might be of inflationary origin, if we measure a signal in this region, then the origin of magnetic fields in galaxies cannot be from inflation alone. They have to have some help from galactic dynamos. It could be further generation by galactic dynamos or some amplifications by galactic dynamos. On the other hand, if you detect magnetic fields in this region, in the red region, then the origin of magnetic fields in galaxies must be from inflation. They might have been further modified by dynamos, but inflationary magnetic fields are good enough to explain the magnetic fields in galaxies that we observe. Now, the joint Planck SPT puts an upper bound here. CMB-S4 will bring it down to 0.12, and CMB-HT will reduce it to this level. So you can put a very tight upper bound by looking at the anisotropic birefringence measurements and the effects of primordial magnetic fields in that. So this signal to noise ratio of 3 tells us that we can detect, so CMB-HT has the capability to detect inflationary, scale invariant inflationary magnetic fields at the 3 sigma level. So if you do not detect if you detect inflationary magnetic fields at the 3 sigma level, you're essentially detecting inflation at the 3 sigma level, which is something CMB-HT will have the capability to do. Now, this is all fine and good, but the problem with observations is that if you're looking at the CMB photons that are coming to your detector, these CMB photons are passing through the rest of the history of the universe. And before hitting our detectors, it's passing through all of the Milky Way before hitting our detectors. And our Milky Way has a micro Gauss level magnetic fields. And any galaxy has a lot of scattered magnetic fields. So if you're detecting an anisotropic birefringence, how can we be sure that the signal that we detect is from the CMB? So it's from the primordial magnetic fields. It's the CMB photons passing through the primordial magnetic fields right after recombination. And it's not the anisotropic birefringence when it's passing through the galaxy. Because magnetic fields in our galaxy can also lead to birefringence of 10 to the minus 5 degrees squared, similar to 0.1 nanogauss magnetic field. So they'll have the same effect. So how can we distinguish between them? So we need to somehow subtract the birefringence caused by the Milky Way. And the question is, can we do that? Can we confidently subtract the birefringence caused by the Milky Way? And it turns out that the magnetic field of the Milky Way has been very well mapped. So there's this NVSS catalog, which has measured the birefringence in the Milky Way from extragalactic radio sources, around 40,000 extragalactic radio sources just outside the Milky Way. So you're looking at the radiation by these radio sources. They are also getting polarized as they're passing through the Milky Way. And since you have a huge number of sources that you are looking at, you can calculate their birefringence and get a very nice map of the Milky Way. And these radio sources are also measured at multiple frequencies, which makes the map of the Milky Way birefringence more precise. Because since things are passing through magnetic fields, you need to measure them at least at 2 different frequencies. Now, this is what the basic picture is. So this is the CMB, the photons are coming from there and hitting our telescopes. They are passing through the primordial magnetic field, which is the strongest right after the CMB is formed. So we need to find the effect of this, but they are going to pass through the magnetic fields in the Milky Way, and we need to subtract out the effect of this. And these are the extragalactic radio sources, which have been used to basically map out very precisely the galactic magnetic field. So these radio sources, they are modified only by the galactic magnetic field and not by the primordial magnetic field. So we can get a very nice constraint and handle on the strength and of the galactic magnetic field. Now, if you do the analysis, you'll see that the galactic magnetic field has an associated error bar of 0.006 nanogauss, which is much, much smaller than the 0.036 nanogauss on the primordial magnetic fields that we are getting from CMB-HT. So you can very confidently subtract out the Milky Way birefringence contribution to any contribution from primordial magnetic fields. So to reiterate, the constraints on primordial scale invariant magnetic fields from Simon's observatory is 0.47, from CMB-S4 it's 0.08, and from CMB-HT it's 0.036. Now, you can get more updated measurements because as we are talking, people are making more measurements of these extragalactic radio sources in order to constrain the galactic magnetic fields. And this will only serve to lower these bounds even more, so you can get a much more precise subtraction of the Milky Way birefringence contribution. So to summarize, we have the 95% 2 sigma confidence level upper bound on magnetic fields at 1.2 nanogauss, and that comes from looking at the TE spectra by Planck and the BB spectrum of the CMB from the South Pole telescope. Now we are measuring the amplitude of anisotropic birefringence, and the plan is to measure it from using CMB-HT and the planned CMB, the CMB-S4 and the planned CMB-HT, and they are basically tightening it to 0.16 and 0.072 nanogauss respectively. So these are the 2 sigma confidence levels we are talking about, and these are the 1 sigma, so the 2 sigma levels are twice that. And the interesting thing is that the CMB-HT bound, that's going to be below 0.1 nanogauss threshold. So this being below the 0.1 nanogauss threshold, so we can use CMB-HT to essentially distinguish between a purely inflationary scenario of galactic magnetic fields or a dynamo origin of the galactic magnetic fields. If we detect scale invariant magnetic fields below 0.1 nanogauss, that will point us to a dynamo origin of the galactic magnetic fields. Whereas if we detect something above 0.1 nanogauss, that will be a compelling evidence for inflation. And CMB-HT, because its error bar on the magnetic field is 0.036, it's capable of detecting primordial magnetic fields at 3 sigma significance, which means it's capable of detecting inflation itself at 3 sigma significance. Thank you.
So thank you very much
Sure.
for this nice presentation. And if there are any questions, please unmute yourself and ask.
I have a brief question.
Sure.
Yeah, earlier in your talk at the beginning, you mentioned there are dozens of models of inflation that can generate this desired magnetic field. Can you give an example of how that works, maybe for a couple of minutes, how that mechanism works?
Sure. So, dozens of models of magnetogenesis. So not technically of inflation.
Right.
So,
magnetogenesis, but based on inflation, I imagine, right?
Yeah. So let me go back to this slide. Where I have this coupling. So the most common model is something like this. So you have this scalar inflaton field, and you couple this hypermagnetic field, because this is before the electroweak phase transition, but that's just related by principle. And now you take different forms of this coupling depending on, so you can back engineer what the form of this coupling will look like. Depending
that's what
on
I was looking for. Yeah, that's what
So you can basically back engineer this. So you take a generic coupling, say f of phi, and you can calculate the stress energy tensor, and then you can calculate the T00 component, which gives you the magnetic field strength. Let's forget the electric part for a moment, because that also becomes important later, the electric part. But for the moment, if you consider just the magnetic part of the stress energy tensor that you get from this kind of coupling, you can write the stress energy tensor in terms of this f of